The topic for this lesson is the AND and OR gate. The output of a bipolar junction transistor amplifier, for instance, may be adjusted anywhere between 0 and V sub cc by applying the proper input voltage. Such circuits are called analog circuits since their output values are analogous to their input levels. There are, on the other hand, circuits designed to operate in one of two states. A switch is either on or off, a pair of relay contacts is either open or closed, and an amplifier can be designed so that its output has only two values, high or low. The two digits 0 and 1 are commonly used to denote the two states of such circuits, and they are therefore called digital circuits. The principles of digital circuits are derived from the theory of mathematical logic, since logical statements can also be in only one of two states, true or false. As a result, digital circuits are also called logic circuits. The application of digital circuits in the early days was confined to relay networks and digital computers. But the advent of IC technology, especially MOSFETs, has made it possible to fabricate extremely complex and powerful digital subsystems in tiny packages. The small size and high versatility of digital ICs have led to the widespread use of digital circuits and systems, even in areas that used to be the strongholds of analog circuits. Digital circuits can be classified into four categories: SSI, small-scale integration; MSI, medium-scale integration; LSI, large-scale integration; and VLSI, very large-scale integration. SSI circuits contain several gates in one chip. MSI circuits contain 10 to 100 gates on a chip and perform complete logic functions. LSI circuits contain more than 100 gates on a chip and perform complex logic functions, and VLSI circuits contain thousands of gates on a single chip and are complete digital subsystems. The trend in modern logic design of digital systems is to use the largest level of integrated circuits practical to conserve space and simplify the approach to the design. The inputs and outputs of digital circuits are restricted to be at one of two voltage levels, such as, for example, 0 volts and 6 volts. The two levels are simply referred to as low, abbreviated L, and high, abbreviated H, regardless of their actual numerical values. The designer and the manufacturer define the input-output characteristics of an actual logic circuit in terms of low and high, L and H. The assignment of logic 1 and logic 0 to the voltage levels can follow any one of the three conventions: positive logic convention, negative logic convention, and mixed logic convention. In positive logic convention, H equals 1 and L equals 0. In negative logic convention, H equals 0 and L equals 1. In mixed logic use, some parts of the circuit use positive logic and some negative logic. Each input and output is denoted by an algebraic variable, x, y, etc., and is called a switching variable. There are three basic operations in switching algebra: logic sum, logic product, and complementation or inversion. The digital circuits which perform these operations are called gates. The addition operation in logic is governed by the following rules: 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 1. If x and y are designed as the switching variables, their logical sum is denoted by x plus y. The operation of the logical sum is also called the OR operation, and the OR gate is represented by the symbol illustrated. There are four possible combinations, and these are tabulated in a form known as a truth table. The truth table for a two-input OR gate is now shown. The OR operation conforms to the associative law as illustrated. The inputs may be grouped in any manner and the sums are not affected. The outputs for an OR gate with inputs M and N are now shown. The operation of multiplication in logic is governed by the following rules: as 0 times 0 is equal to 0, 0 times 1 is equal to 0, 1 times 0 is equal to 0, and 1 times 1 is equal to 1. With x and y as the switching variables, the output is shown in the following illustration. The truth table of the AND operation is now shown. The AND operation conforms to the associative law as shown. The outputs for an AND gate with the inputs M and N are now shown.